Hello everyone, welcome to the electromechanical devices course. In this video I'm gonna solve some examples on the steady-state sinusoidal circuit analysis, and I'm gonna show you how we can apply the node voltage analysis method and the mesh current method to do analysis for this or steady-state analysis of electrical circuit. Nothing would be new in terms of the analysis of the electrical circuit when we apply the node voltage method or any other method of the form method that we explained in chapter 2. Your objective is just to, what I recommend or advise you is just to give a revision before you deal or handle any problem that already covered in chapter 5. Chapter 2, we already discussed 4 different methods of doing analysis of the different electrical circuits. So your objective is just to revise them, and you're going to stick this to the same procedure that we explained in the chapter 2. But the new thing is going to be how you solve the equations. Once you drive the equations, your objective is just to solve them. But these equations will be dependent on complex numbers, so that's why in chapter 5 we revise first and we discuss the mathematics behind the complex numbers and how we can perform different operations to these numbers. So your objective is just to memorize these things also on that we covered regarding the complex numbers when you solve the equations. As conventionally we do in the analysis of electrical circuit, that we start with driving some equations that represent the electrical circuit. These equations are the circuit equations using one of the 4 methods that we explained in chapter 2. Then once you end up or find the equations, your objective is just to solve them. So since this equation that we already, like this example that I'm going to show you here, includes some complex number, you have to know how you can do operations over complex number to solve the equations. But driving the equations themselves will not be new, or it won't gonna be different than the thing that we already covered in chapter 2. Make sense? So that's why I advise you first to revise chapter 2 before you tackle any or consider any problem in chapter 5. Make sense? So, and also another advice is try to work in the simple form. Like even if you're given something in the numerical form, don't substitute with the values. Stick to and keep using these symbols till the end of the problem. Try to make the symbols or to use the symbols as much as you can. This is going to make the problem much, or simplifying the equations much more easy. So your objective is just, you're going to end up with some equations, then your objective is just to simplify this equation into their simplest form, in the symbolic form of the equation's parameters. Then your objective is just to substitute at the end, as typically as I'm going to show you through this example. For this example, we already given this electrical circuit with 2 sources. One is a voltage source and Vs. This Vs is given as a sinusoidal function as 20 cosine 3. This is the omega t plus 90 degrees. This is the phase angle, and there is another current here which is given as 3 amperes, which is a current source. And we do have resistance with 5 ohms. We do have also the Henrys, which is this inductor or inductance of this inductor, in addition to the resistance by 5 ohms. And there are some mesh currents that already roaming within this mesh and this mesh, or within this loop or this loop. So it is required here is to apply the node voltage analysis method. And if you remember that this method depends on identifying node voltages for these nodes, and the main target is just to find the voltages first. Then once you find these voltages, your objective is just to work over the requirement as typically the same thing that we did in chapter 2. So using this method, you are required to find V1 and V2, V1 and the phasors, V1 and I1 for the mesh current, and V1, which is the node voltage as shown here. So what we're gonna do first, your objective is just to apply. So the first thing is just apply the node voltage analysis method to this electrical circuit. And if you remember that this method depends in the first step, your objective is just to identify nodes, to the different nodes within the electrical circuit. If we did so, we do have one node here, we do have another node, we do have a third one, and in addition we do have these nodes, which would, all of these nodes could be considered like the reference node. So we can set up here like a reference node. Then your objective is just to give numbers to these different nodes. As you can see, like all of these nodes, as we discussed in chapter 2, they can be merged to one reference node, which is this reference node that we used to give it like V0, by the way. But since we have here V1, we can give here, for example, V0 and V2. Or even you can use like V2 and V3, give any names the way that you want. In addition, you should understand that there should be a reference here. So this is the first two steps actually, that to locate the nodes, then you assign voltages to these different nodes, including even the reference node, which is V0 or whatever. So this is our reference, and we give like V0 for this node, V1 and V2. Then your objective is just to define the voltages over the different electrical element. Like we do have this voltage source, so there should be a voltage over this source, and there should be another voltage over this current, and there should be a voltage over this resistor and over the inductor, and there should be a voltage over this resistor. So we can give names to these voltages, like let us give it like Vx, and this is like Vy, as we used to do. And definitely this is going to be V2, because this should be V2 negative V0, moving from 0 going to 2. So it's going to be V2 negative V0. And V0 is just a 0 or a 0 reference or a 0 voltage. So definitely this is going to be V2. And this is going to be V1. The voltage here is going to be just like kind of V1. And the voltage here is going to be like V0 already. And something that you should understand about this electrical circuit, that V0 is already equal to Vs, because the voltage over this electrical element is already a voltage source which is equal to Vs. So you should note that V0 already, we have it already with the Vs value as already given to us here. Make sense? Now we have to work how much is Vx in terms of the voltage nodes. This is what we basically do. The next step in the node voltage is to give the voltages over the elements in terms of the voltage nodes. So like Vx, how much it is in terms of V1 and V0. So as we did in chapter 2, Vx, it should be V1 negative V0. It moves from V0, the low voltage, to the high voltage, so it should be V1 negative V0. The same thing, Vy, it's going to be V1 negative V0. And by the way, we just make up these directions. You can assume any direction, it's up to you. So your objective is just to write an equation here for Vx. It should be V1 negative V0, and this is going to be like one kind of equation 1. And we do have another equation that Vy, it should equal to the V1 negative V2 according to the directions that are assumed up there. Make sense? So we do have everything. Now we can apply the Kirchhoff current law to these three different nodes, but you have to figure out how many unknowns, how many equations do you need, and the number of equations depends on the unknowns. And the main unknowns here that we are seeking are the node voltages. We do have three node voltages. We do have V0, and we said that V0 is already Vs, and Vs is already given. It means that V0 is already there. So there is no need to write an equation for V0 because we already have it. But we still need two equations to figure out how much is V1 and V2. So that's why we need just two equations. How we can figure out these two equations? Your objective is just to apply Kirchhoff current law to any two nodes within this electrical circuit. Make sense? So as I mentioned, we need two equations for the two unknowns V1 and V2, but before we do so, we have to convert this electrical circuit. Even you can do this one like the first step before starting applying directly the node voltage analysis method. You can first convert this electrical circuit from the time domain to the frequency domain. We're still working in the time domain here, but we have to convert it into the frequency domain. To do so, for this electrical circuit, we can redraw the electrical circuit in this way. Like we're gonna have here one phasor, one impedance for the coil, or this should be the inductor, right? And there should be another phasor here for the resistance, right? And there should be a phasor for impedance. This is, all of these are different impedances for the resistor, and we should have here a phasor for the current source, which is Is equals. Then we're gonna write the value, how much it is. Also, we need a phasor for the voltage source. So for the current and the voltages, we are using phasors. So we should have a phasor here, Vs equals. So what about the impedance? Let us work over the impedance for the resistor. It should be the same value, like ZR equals R, as we said before, right? So it's going to be like ZR, it's going to be 5 ohms, right? And for the inductor, the 500 is going to be the J, which is going to be the L directly times the J, right? Yeah, ZL, it should be like ZL, as we defined it before, it should be J omega L, where L, this is the impedance, the inductance of the inductor, and omega, this is the frequency of the forcing term, which the input voltage here, which is this omega, which it should be 3. So I'm just gonna do a little bit change here to this 3 value. I'm just gonna put it 1, just to make the calculation more simple. So assuming that this is 1, anyway, if it is 3, you're just going to multiply 3 times 5, so this is going to give us 15 down there. But for the simplicity of the calculation, I'm just going to assume this one, this omega is just 1. But you should understand that the value of omega is already given like 1. But anyway, ZL, it should be omega, J omega L. So J omega is just 1 times L, which is already given by 5. This is going to give us the equivalent impedance or the equivalent resistance in the complex plane of the inductance. And the same thing for the resistor is going to be ZR, is going to be also 5 ohms, the same ZR. So that's why I won't going to distinguish between this ZR and ZR as long as they do have the same ohms. But if this value is different than this one, it is advised to have like here ZR1 and here like ZR2, or ZR as ZR dash. So you have to distinguish, what I mean that you have to distinguish between these two different resistors or these two different impedances as long as they do have two different values. But if they do have the same values, it is advised even to use the same symbol for both of them, okay? How about the IS? This is the phasor. Now we're going to work over the phasor. These are the impedances. The phasor here, it is already given by 3 ampere. So 3 ampere is just a constant. There is no sinusoidal form. So this should be like a real value. So real value, it means that it should be like 3 angle 0. If we decided to write a complex number or a real number in the complex plane, or in the polar form, it should be 3. This is the real value, the magnitude of the given real value, which is just as it is, and the angle should be 0. Because if we expanded this one into the trigonometric form, like cosine 0 is going to give 1, and sine 0 is going to give us 0. So the J term will be 0, will be eliminated. That's why we do have a real number here, a 0 angle. This is for the phasor IS. And for the VS, the phasor form of this one, your objective is just to get rid of the cosine and omega t and just use the 20 and the 90 degrees. So this phasor form, and the phasor form is going to be the 20 angle 90. It's going to be 20 angle 90 degrees as already given here. So I've converted, and definitely we're going to have here the I1 or the phasor, which is already rotating here, which is required I1, and we do have here another phasor which is I2. It is required to find V1, this V1, and definitely as we defined, this should be like V2, and this is the V0 that we defined up there. Make sense? And even if we just wrote the others, like here we should have the Vx, since we're gonna work over this form. So I'm just gonna move this one down to have a space to represent the voltages Vx and Vy. So this is gonna give us here the Vx, this should be the Vx, and this should be the Vy as we define it, and definitely this should be the V2, right? And we should have here like kind of V1 going in this direction, but anyway we do have the current already, and we do have here the V0, right? This should be the V0 that we already have it. So then you're just gonna continue working. So you can do these things here, build this, convert to the frequency domain even before you start applying the node voltage analysis method, or you can do as I did here. So now we're gonna work over the node voltage analysis, and remember that we just need two equations for V1 and V2. So we're just gonna apply for node 1 and node 2 the Kirchhoff current law. So the Kirchhoff current law, starting with for node 1, how it's gonna look like. So your objective is just to sum the current. So the current here, it should be coming in, it should be entering the node, it should be positive. The current due to Vy divided by ZL, it should be positive, and this current is leaving, so it should be negative this Is. So if I decided to apply the Kirchhoff current law to the first node, this is gonna give us the Vx, but divided by ZR, because as you remember, according to Ohm's law, that the V over R or V over Z, since we're already working in the frequency domain, it should give us the current over this branch, which is going to be the Vx over ZR. It should be positive because it enters the node, and Vy plus should also be positive because Vy entered the node over ZL. This negative, this should give us negative Is, which is this current equals 0. As you can see, I didn't substitute with values. I'm working in the simple form, and this is what is recommended. This should give us the first equation, but let us do some simplification first over this equation. One of the things that we can get rid of the denominators by multiplying by their multiplication. So what I'm going to do here, I'm just going to multiply this equation, multiply by the ZR times ZL. So I'm going to multiply all the terms times this value to get rid of all the denominators. So we're going to end up here with Vx. This is going to give us Vx definitely times ZL because the ZR will be cancelled, plus Vy times ZR negative Is times ZR times ZL equals 0. And this should give us the first equation. So this is the first equation, or let us use equation 3 because we already defined here equation 1 and 2. Or even we can substitute, we still need to substitute for Vx and Vy by their values according to equation 1 and 2. So substituting 1 and 2 into this equation, we're going to end up, Vx is already V1 negative V0. So this is going to give us V1 times ZL negative V0 times ZL plus the Vy, which is already V1 negative V2. So this is going to give us V1 times ZR negative V2 times ZR negative Is ZR ZL equals 0. Do more simplification, try to collect the node voltages that we are seeking in one terms, like we do have V1 and V1 here, so collect them. So we're going to end up with V1 times ZL negative, positive ZR plus ZR negative the V0 ZL negative the V2 ZR negative the Is ZR ZL. They should give us 0, and we can give a number to this equation. This is the first equation for the first node. This is one of the equations that needed to be solved for V1 and V2. We need another equation that we can get by applying Kirchhoff current law, but for node 2. For node 2, we do have only two currents. One is leaving, one is entering the node. So V2 is going to be positive, V2 definitely over ZR, and Vy over ZL is going to be negative. So this is going to give us the second equation, which is a very simple equation, V2 over ZR positive negative Vy over ZL equals 0. So multiply to get rid of the denominator by ZR times ZL, all the terms. So this is going to give us the V2 times ZL negative Vy times ZR equals 0, right? Then we can substitute for the Vy. This is going to give us the V2 negative ZL negative the Vy, which is already V1 ZR positive V2 ZR equals 0. Then we can collect the terms that include, there should be times that include the V2. So this is going to give us V2 times ZL plus ZR. We can even move this one to the other side to be like V1 times ZR, and this is going to give us the second equation, which should be like equation 4 according to the order. But these are the two equations that should be solved for V1 and V2. So we can start from equation 4. So now we can work according from equation 4. We already have here, we can come up that V2 equals, or we can start with V1. For example, it's up to you. You can find V1 equals the you're just gonna divide by ZR, so it's gonna be like ZL plus ZR divided by ZR. This should be multiplied times V2. Then you can substitute this expression into equation 3 to end up with one equation and one unknown, and this unknown is going to be V2. So plugging here into the third equation, remove V1 and substitute with this value. So you're going to multiply this parentheses into time this one. So this is going to give us the ZL plus ZR divided by ZR. All of this should be multiplied times ZL plus ZR. So this is just the first term. Negative V0, all of these negatives we can move them back except the V2 because we're already collecting V2. There should be here V2, right? This is the first term. So we still have here negative V2, negative V2 ZR, right? So these two terms we can collect them together into one term if we take the V2 as a common factor, right? So considering V2 as a common factor, so we're going to end up with like negative ZR as a square bracket here and multiply times V2. So this is going to be this term plus this term. Now the other terms, we're going to move them to the right side. And remember that V0 we already have it, IS we already have it. So we have everything except V1 and V2. So in this equation, we're going to end up with only one unknown. This should be V0 times ZL and times ZL plus the IS times ZR ZL. So this expression, this equation, now it should be solved for V2, right? But to solve this equation, you should have ZR, ZL, and we already have them, and we have everything. We have only one unknown. So if we divide it by this term, we're gonna end up with V2. So simply we can say that V2 automatically is gonna be the V0 times ZL plus the IS times ZR times ZL. All of this should be divided by this term, which it should be the ZL plus ZR times the ZL plus ZR divided by ZR negative ZR. This should give us the V2, right? So now your objective is just to work over the complex number. To find Z2, your objective is just to substitute with the Z values and do the calculations and the operations over the complex numbers. And this is what we're going to do. So as you can see, one of the operations here is the summation of the addition of the ZL plus ZR. So let us work over these different calculations, starting with the ZL plus ZR, how much it is. ZL, we already got it. I'm just gonna recall here the ZL value, which is already 5J as we defined it up there, and the ZR, it is already 5. Remember that this is in the rectangular form. In the phasor form or the polar form, this J5, it is equivalent to 5 angle 90 degree. The positive 90 gives positive J, the negative 90 gives negative J. If there is no J, it means that the angle automatically is going to be 0. If this value is negative, the angle is going to be 180 degrees. So this is simply how we can, this is the rectangular form and this is the phasor form or the polar form of the complex number. So these are the Z's that we already have here. The impedances, we don't have any impedance for the capacitor. So your objective is just to plug these Z's here to do this calculation. Like the addition over two complex number, we said that it should be done in the rectangular form. So that's why I'm just going to substitute for ZL by J5 in the rectangular form plus ZR, which is already 5. So then I'm going to convert this one. So this is the rectangular form, which is just 5. This is the real, the imaginary term is just 5. And what about its equivalent? What about its equivalent polar form? It's going to be the square root. It should be the square root of the 5 square plus the 5 square. And the angle, it should be the tan inverse of 5 over 5, right? If we did this calculation, this term is going to give us the, so I'm just going to put the numbers directly. This term, the magnitude or the peak, is going to be 5 square root of 2. And the angle is going to be 45 degrees if we did the calculations. Make sense? Also, we're going to continue working over the other operation. Like now we already did this part. Now we have to divide by ZR. So the ZL plus ZR that we already got it in the polar form, with this value, or divided by ZR equals ZL, it is 5 square root of 2 angle 45 degrees, which this numerator term that we just calculated, and divided by the ZR, which is already 5 angle 0 in the polar form. We said that division multiplication should be done, it is better to be done in the polar form. So that's why we can simply do the division 5 by 5 divided by 5 would be cancel square root. So we're going to end up with just a square root of 2, and the angle is going to be 45 degrees. This is going to give us this term, right? Then even we can subtract the ZR from, we can do the multiplication of this term times this term, then we are going to subtract to finish all the denominator, and this is what we're going to do. So we're going to have here the multiplication of ZL plus ZR. This should be multiplied times the ZL plus ZR divided by ZR that we just got it, negative ZR. So we got this term by 5 square root of 2 angle 45 degrees. This should be multiplied times the square root of 2, which this term angle 45 degree, angle 45 degrees. Then we are going to subtract the 5 angle 0, right, which is this ZR. So doing the multiplication first, it should be done in the polar form. So this is definitely is going to give us 10. 5 square root of 2 times square root of 2 gives 10. And then you're just going to sum the angle. This is going to give us angle 90, negative 5 angle 0. Then to do this subtraction, it should be done in the rectangular form. What is the equivalent rectangular form of angle 90? It is J, positive J gives positive J the same magnitude value, which is 10, and the 0 gives a real number of just 5. This is just like nothing, right? Multiply times 1. So this is going to be the polar form of this operation. Then you're going to convert it back to the rectangular form, this is the rectangular form, then you're going to convert it back into the polar form. And to convert to the polar form, it's going to give us the square root of this real value square plus the square of the 10, and the angle, it should be the tan inverse of the imaginary value, which is 10, divided by the real value, which is negative 5. So doing the calculations, this is going to give us this term will be, we already got it here by 11.18, and the angle we got it by the negative 63.45 degrees. Make sense? So this should give us the denominator of this term. We got all of this denominator. Now we still need to do this operation, ZR times ZL. One more operation to go to substitute and to find V2. So we need to multiply ZR times ZL as already given. ZR, we already got it by, it is already given by 5 angle 0 times the ZL, which is, sorry, how much it is? It is already 5, I think, yeah, 5 angle 90. The multiplication should be done in the polar form. So angle 90. Doing the multiplication definitely gonna give us 5 times 5, 25, and then we're gonna sum the angles. So 0 plus 90 is just 90. Then if we plugged all of these operations, 1, 2, 3, 4 operations, plug them here, you are in a good shape to find the V2. So now we can find V2, then V2, or you could say like, let us give it like a number. This should be equation 5, I think, right? This should be equation 5. So now we are going to substitute, just substitute into equation 5. So we're going to end up with this, that the numerator, we already have V0, remember, now we are going to substitute for V0, it should be Vs as we mentioned, and Vs in the phasor form, we already got it here by 20 angle 90 degrees, right? So we're just going to substitute this value here, which is 20 angle 90 degrees, this is V0, times ZL. ZL in the phasor form, it is already, there should be 5 square, angle 90 degrees, plus the IS. IS, we already, in the phasor form, it is already 3 angle 0, right? So it's gonna be 3 angle 0, 3 angle 0 times the ZR times ZL, right? ZR times ZL, which we already got it here by the 25 angle 90 degrees. This should be the numerator. The denominator, we already got all of this term, which is this value, we got it by 11.18 angle negative 63.45. So still there are still more operations that should be done here on the numerator. Like here, the multiplication of 20 times 5, this is going to give us 100, and then we're going to add the angles. This is going to give us 180, plus the 3 times 25 gives 75, and then we're going to add the angles, going to give us 90 degrees, divided by the 1118, and the angle is negative 63.45 degrees. Then you have to do the summation over the numerator. It should be converted to the rectangular form. The rectangular form of the angle 180 gives negative 1 times 100. So this is, and there is no j's. And this one is going to give us the positive j angle 75 divided by the 11.18 angle negative 63.45 degrees. Now you have to convert this term into its equivalent polar form. Into the polar form, this term will be into the polar form. This is going to give us the square root. It should be the square root of 100 square plus the 75 square, and the angle is going to be the tan inverse of the negative 100 divided, or the, I'm sorry, the negative 75. It should be the imaginary term first divided by the 100. So doing the calculations, we're going to end up with this value for the, for on the top here is going to give us 125, and the angle is going to be the negative 36.8 degrees. And the denominator is still 11.18, angle the negative 63.45 degrees. Then we're going to do the division by dividing 125 by 11.18. This is going to give us also 11.18, and the angle, subtract the angle negative 36.8 negative, so this is going to be positive 63.45. This is going to give us a positive value of 26.6 degrees. So this is going to give us V2, how much it is. Now this is one of the phasors. Now to find V1, we have to substitute into equation. Let us give it a name like equation star, which should be this equation here. We already defined before V, this expression. So how much is V1 in terms of V2? We got V2 simply, if you plugged into this expression star, you're going to end up with V1, and this is what we're going to do. So we have to multiply V2 that we just got it by ZRL plus ZR divided by ZR, and this term we already got it by square root of angle 45 degree. So this is what we're going to do. So from here, we're going to end up that V1, it should be the term which is square root of 2 angle 45 degree, which is ZL plus ZR divided by ZR. This should be multiplied times V2 that we just got it by 11.18, and the angle is 26.6 degrees. This is going to give us, doing the multiplication, definitely this is going to give us the V1. And simply we're going to do the multiplication in the polar form as we already have it here. So it's going to be 15.812. And this is the magnitude, and the angle definitely is going to be 71.58 degrees after you sum these two, or let's say it's going to be like 0.6 degrees after you sum these two numbers together, right? So this is going to give us the phasor V1, and this is the first requirement. It was required to find, this is the answer here. Okay, this is one of the two answers that we are seeking. Also, we still need to find the phasor over the mesh current phasor here, which is I1, how much it is in this I1. So I1, simply, according to the mesh current method, I1, it should be like, it should be the current over this branch, like the current over this branch definitely is going to be this I1. Then, but the current over this branch will be the difference between I1 and I2, right? But anyway, the I1 or the current over this resistor or over this impedance definitely is going to be equal to the, so this is the mesh current. You should, I'm sorry, this is the branch current and this is the mesh current. For over this element, the mesh current and the branch current both are equal. So I1 will equal to the branch current over this impedance ZR. So simply, how much is the mesh current I1? It's going to be the current over ZR, and the current over ZR, it should be Vx over ZR according to the node voltage analysis method, right? So according to this method, we do have I1, it should equal to Vx divided by ZR. So this is the expression that we're going to use down there, right? And we do have everything. We already got Vx. Remember that Vx is already V1 negative V0, and we just found V1 and we already have V0, right? And this is what we're gonna do. So simply here we're just gonna work over the phasors. Here find the phasors I1. So simply, as we agreed, at I1 it should be Vx divided by ZR, and in the meanwhile Vx it is V1 negative V0 divided by ZR. So how much is V1? V1 we got it by 15.812, and the angle is already 71.6 degrees, and this should be negative the V0, which is already given by 20 angle 90. This is the V0, which is Vs, and this should be divided by 5 angle 0, which is ZR. Then your objective is just to do the calculation. So this definitely gonna give us I1 equals. We have to convert to the rectangular form. So this is gonna give us 15.812 times the cosine of this angle, which is 71.6 degrees, plus J sine the angle, which is 71.6 degrees. This is just the first term. Negative the rectangular form of the angle 90, it is very simple. It is directly J20 divided by the denominator, which is just 5. If the angle 0 gives 1, so this is gonna give us like 1 times 5, it's just real value as 5. So this is gonna give us the rectangular form, or even we can leave this one in the polar form as long as we're gonna do the division, so we need it in the polar form. But we need just this term on the top here, it should be in the rectangular form. And this is what we did, we expanded into cosine and sine. Then you're gonna do this calculation, so you're gonna end up with a real number plus J, an imaginary number. So if we did the calculations, we're gonna end up with 15.812 times the cosine 71.6. This is definitely gonna give us 5. If we did the calculation real plus the imaginary term, we're gonna get it also by 5. If we did the calculation here, we're gonna end up with, 15. So this should be J15. And negative the J20, which is this other term, all of this, it should be divided by 5 angle 0 degrees. Then your objective is just to collect the J's terms, so this is gonna give us 5 negative J5 divided by the 5 angle, how much? Angle 0, right? Then your objective is just to do the calculations here to convert this one into the polar form. So the polar form is going to give us 5 square root of 2, which is this 5 square plus the 5 square under the square root is going to give us 5 square root of 2, and the angle should be the tan inverse of negative 1. It should be the tan inverse of the negative 1, which is going to give us the negative 45 degrees, right? This should be divided here, then we're going to end up with 5 angle 0. So if we did the calculations, this definitely is going to give us I1, the phasor, as the 5 will be cancelled. Then we're going to end up with just a square root of 2, and the angle negative 45, negative 0, just going to be negative 45 degrees. So this is going to be the phasor I1 in the phasor form. Make sense? If we decided, and this is it's going to be the answer number 2, if we decided to convert this phasor forms for V1 and V2 into the sinusoidal form, so we're gonna have here like the voltage V1, how much it is in the time domain. So V1 we already got it by the 15, this is the magnitude, and this should be the angle. So definitely it's going to be the 15.812, which is the magnitude, and the angle, it's going to be just going to add here the cosine. The omega 2 is just 1, so it should be t, plus the angle, which we got it by 71.6 degrees. This is going to give us the phasor V1 in the time domain, and the I1 of t, they should be like a function of t, by the way, and the current I1, the mesh current I1 in the as a function of time is going to be the magnitude, which is square root of 2, and the cosine of the omega t, which is just 1t, plus the angle, which is negative 45 degrees. So this is going to give us these two in the time domain. This is in the time domain. Make sense? So this example, this is a typical example that of the thing that you should do when you do analysis for sinusoidal analysis for electrical circuit. Your objective is just to convert the electrical circuit first into the frequency domain from the time domain or the frequency domain, and you're gonna stick to the procedure that we explained for any method that you're gonna use through chapter 2. And my advice is just to work on the simplified form. Try to simplify the parameters. Here we are seeking two unknowns, two main unknowns, V1 and V2. So I simplified them into the simplest form. Then I started working over doing the calculation or the operations over the complex number to end up with these phasors values. And that's it. So this is just the main procedure is just to drive the equations in the simplest form, simplify them in the simplest form, then you're gonna work over the complex number to find the unknowns. Okay, so nothing new in terms of the analysis. It will be typically the same procedure as we explained in chapter 2, but the new thing is how to convert from the time domain to the frequency domain, how you can work over the complex number. So this should require some practicing, and this is a typical example of this case. All right. So how about if I decided to repeat the same example and solve, but using the mesh current method, right? To find the mesh currents I1 and I2. How about if we're interested in I1 and I2? So it is advised to this mesh current, so we have to use the mesh current method. So what I explained here, I showed you how we can apply the node voltage analysis method to do analysis to this electrical circuit to find some unknowns like V1 and V2. Now let us repeat the same example, the same problem, but using the mesh current just to find I1 and I2. So how we can do it, I'm just gonna have a copy of this electrical circuit in the frequency this electrical circuit seems like we're reducing the node voltage. So since we're gonna use the mesh current method, there is no voltages should be here, right? These node voltages V1, V2, and V0 should be removed, right? Now we're gonna work over the mesh current method. So we're gonna apply here, apply the mesh current method to find the currents I1 and I2 in the phasors, definitely. Okay, so if you remember in the process, in this procedure is just the first step is just to locate or define the mesh currents over the different meshes. It's just locate the different meshes in this electrical circuit and assign mesh currents to them as already given here I1 and I2. So this is for the first, these are the first two steps. It's just to assign this within this mesh I1 and I2. Then the next step is just to apply either Kirchhoff current law or you can apply the Kirchhoff voltage law over the meshes that you have. But as you can see, we have here within this mesh or within this loop, if we decided to apply the Kirchhoff voltage law, we're gonna stuck with the problem that we have no clue how much is the voltage over this element because this is current source. And if we decided even to apply it over the second loop, we're gonna still with the same problem that we're facing the same problem that we do have here at current. Another thing that you should count how many equations do we need. We need here two equations. Why? Because we do have two missing mesh currents. I1, we have no clue how much it is. I2, we have no clue how much it is. So that's why we need two equations. So how we can find these two equations, this is the thing that we need to do. Make sense? So the objective is just to find these two equations, but we have to apply like two equations or Kirchhoff voltage law twice. But as I mentioned, we're going to start with this branch. But we had an experience with this one before through chapter 2 that we can come up with another equation that defines the current over this current source. And this current IS, it should be in terms, if we decided to define it in terms of I1 and I2, is going to be dependent on the difference between them, because over this current, as you can see, if we continue the rotation of I1, I1 is going to be going down, and according to the direction that we consider for I2, I2 is going to be going up. So IS, for this case, it should be the positive of I1, negative the I2, because the I2 is opposite to the direction of the IS, while the I1 in the same direction. So this is going to give us the first equation, like this is one of the equation. And then the second equation, you're just going to do apply Kirchhoff voltage law to the super mesh, that you're going to skip this branch and do the apply the Kirchhoff voltage law to the entire electrical circuit, the big loop. And this is going to give us the second equation. So here, what we're going to do, the first equation that we need, equation 1, definitely we're going to make use of this information regarding the current, that the fact that IS should equal to the I1 negative I2. This is going to give us the first equation. And as for the second equation that we needed, we have to apply the Kirchhoff voltage law, but for the entire electrical circuit, excluding this branch here of this current source. So Kirchhoff voltage law to this super mesh, this gonna give us Vs, it should be negative Vs because it is input source, right? And we're gonna have here this output, which is the plus the voltage over this resistor or over this impedance, which it should be the current passing through it, which is I1, because the current over it is I1 only. There is no effect to the I2 over this electrical element, times ZR. This is going to give us the voltage here, and it should be positive because it is output. Then how about the voltage over this ZL? It should be I2 because the current over ZL is going to be only I2. There is no effect of the I1 over the ZL. So this is going to give us the positive as well. The I2 times the ZL. And also the voltage over this one is going to be positive because it is output. Also is going to be the I2 times ZR because there is no effect to the I1 or of I1 to this element. All of this should equal to 0. So we have 1 volt, second, third, fourth. So 4 voltages. We summed all of them together to end up with the second equation according to Kirchhoff voltage law. And this is the second equation. Now we have two unknowns, I1 and I2, so we have to work over to simplify this equation. So simply we can start from equation 2. We can start with equation from equation 1. We're going to end up that, let's say that I1 and move I2 to the other side. So this is going to give us IS plus I2, right? Then you can simply plug it here into the second equation, into equation 2. So if we substitute it into equation 2, this is going to give us the negative of Vs. The I1 will be substituted by the positive ZR times I1, which is just IS plus I2, right? This is the second term, plus we do have I2ZL plus I2ZR equals 0. Then your objective is just to collect the I2 terms because for this equation we have only one unknown, which is I2, but IS we already have it, and Vs we do have everything except I2. So collect the I2 terms. So this is gonna give us I2 times ZR. There is one ZR here, right? And there is another ZR, so there should be like 2 ZR. Make sense? Plus the ZL, just collecting all the I2 terms. And this, and move the other terms to the other side. Vs is going to be positive, negative the ZR times IS. Then you can divide by this term to end up with I2. So simply this is going to give us I2 as Vs negative ZR Is divided by the 2ZR plus ZL. As you can see, I'm working in the symbolic form. Now we got the I2. Once we find the I2, we can plug it here into this expression to end up with the I1, right? But we need to find I2 first. To do so, we have to do these calculations in the denominator. You can do it directly by plugging here, or you can do it on a side. It's up to you. So I'm just going to substitute directly because the calculation is very simple. VS is already given by 20 angle 90 degree. This is the voltage source as given up there for the electrical circuit. This VS makes sense. And we already have here ZR, if you remember, it is 5 angle 0 degrees times IS, which is already given by 3 angle 0 degrees. This should be divided by the 2 times the ZR, which is 5 angle 0 degrees. So this term actually can be written as 10 angle 0, right? 10 angle 0 directly. This is the double of ZR plus the ZL, which is already 5 angle, because since we're gonna do like, or let us write like in the phasor form as angle 90. This is the ZL. Then we have to do this multiplication. This is gonna give us the 20 angle 90 degrees, and we do have here 15 angle 0, 0 plus 0. All of this should be divided by the 10 angle 0, and we do have here plus the 5 angle 90 degree. Then we have to do the summation and the subtraction on the top and the denominator. So we do have here, we have to convert to the rectangular form. This 20, 90 is going to be J20, negative 15 is just real, divided by the, this is going to be real, this is going to be plus J5. Make sense? Then we're going to convert this one into the polar form. This is going to give us the square root of the 15 square plus the 20 square, and the angle definitely is going to be the tan inverse of the negative, or the 20 divided by the negative 15. All of this should be divided by the square root of 5 square plus 10 square, and the angle is going to be the tan inverse of the imaginary, which is 5, divided by 10, right? So doing the calculations, simply we're going to end up with these values. So doing the calculation, we're going to end up with the 300 and the angle negative 53.13, and the denominator will be 11.18, and the angle 26.6 in the polar form. Then doing the division, we're going to end up with the I2. So simply I2 is going to be, if we did the calculation, 300 divided by 11.18, going to give us 26.84, and the angle, if we did the subtraction, negative 53, negative 26, this is going to give us the negative 79.73 degrees. So this is going to give us the second phasor, the I2. We still need to calculate I1, right? So to do so, we're going to plug it here. We're just going to substitute into this equation to find I1. So then I1 is going to be, accordingly, I1 is going to be the IS, which I1 is going to be the IS, which is already 3 angle 0, and plus the I2, which is 26.84, and the angle is already negative 79.73 degrees, right? Now we have to work over this summation, so we have to convert these terms into the rectangular form. This one is going to be just 3 real, but this term will be 26.84 times the cosine of the angle, which is negative 79.73 degrees, plus the j sine the angle, which is negative 79.73 degrees. Then you're just gonna do these calculations to end up with one real and one imaginary number, and this is what we're gonna get in this form. So doing the calculation, we're going to end up with this is the real, which is 3 plus the 26.84 cosine this angle. We're going to end up with this value. Then the 26.84 times the sine, this is going to give us this angle, and this negative because the sine rejects the negative sign. Doing the calculation by the square root of this value square plus this value square, and then the square root, this is going to give us the magnitude by the 27.6 0.534, and the angle is going to be the tan inverse of the imaginary divided by the real, which is going to give us the negative 73.58 degrees. So this definitely is going to give us the I1 into this form, 27.534, and the angle is negative 73.58 degrees. So we already got these phasors as already required, and this is the I1 and this is the I2 which were required. So here, through this video or this example, second example, we repeated the same process, but we considered the mesh current method to end up with the I1, the phasor, and the I2 as we already got them here. Make sense? So this is for this example that we already have, that we already did here. It seemed that I did like kind of mistake here or miscalculations when I applied the mesh current, because I should end up with this I1, it should be the same form here, the same value as the current I1 as I got it here using the node voltage analysis method. Yeah, there should be like a mistake here because you should end up with the same phase current phasor I1 and I2. I1 here from the mesh current method, it should be the same value as you're gonna if you are going to solve the problem using the node voltage analysis method. I mean that this value, these two values should be the same. But it seemed that I did mistake in either in the calculation in the voltage node voltage method or the mesh current method. One of the mistakes, for example, that I just located here, which is this calculation, like the square root of this should be squared. So the square root of 15 squared plus 20 squared, and the square root, this one gonna give us 300. So there is a mistake here in this value. I think it's gonna be like 15 squared plus the 220 squared. This is gonna give us the square root, this should be 25. So this is one of the mistakes. So probably there should be some other miscalculations here that I've did, and this what resulted in this value. But anyway, this is gonna be the procedure. Just stick to the procedure. If you're gonna end up with some calculations, it is not a big deal because now we are using some software, so we already making sure of the calculation. But the objective is just to understand the procedure, to understand how we can do the analysis of these electrical circuits using these different methods as we explained through this video. Okay, so that's it, and this is the objective of this video. Again, is just to give you some more examples on the steady state sinusoidal circuit analysis using the node voltage analysis method and the mesh current method. Okay, so thank you and see you in the next video.